GNU plot type of display. Also with dprof, I can collect then dplace information. So with dplace, I can declare statically how many threads to use, how many memories to use, where I want the threads to be on memory, what addresses I want on what memories. And I can also specify page sizes, and we'll talk about page migration as well. All of this stuff is put into something called the MLD, the Memory Locality Domain. An MLD is simply a packet that describes all the topology type information. So when the operating system tries to do something with the program, it looks at the MLD. It's not a hard guarantee. It's going to try to place it where it wants, but if somebody else is already placed there, then you may not get that location. So you can say, I want my application to go to CPU 4 within my system and lock down, and dplace will do all that. There's also the ability of dynamic specifications where I can move virtual addresses to memories or move threads from one node to another. We're not interested in dplace right now. So we've got about 10 minutes, and I think we're okay here. The last piece is environment variables. There are two types of environment variables. We have underscore DSM underscore, and we have OMP or MP. These are the two that I'm just going to focus on right now. The DSM underscore ones are for distributed memory. However, some of them affect multi-threading. Now, we've got a list of environment variables here, but they are documented on the PE underscore environ man page. Man PE underscore ENVIRON for the environment variables in a programming environment. So in there is describing all these variables. A DSM barrier is really part of multi-threading, not DSM. So here we've got some that are for distributed memory. DSM mandatory, DSM migration. What my migration level is. There's something called nmap, must run. I can turn DSM off, or I can place my pages in a certain way. So DSM is memory management. And with this placement, I can say allocate the pages based upon first touch, or allocate the pages round robin across the nodes. Again, first touch is the default. What's the disadvantage of first touch? When I build an array, a lot of programs will initialize or zero the array at the beginning of the program. Then later in the program, they take that array, load it with data, and process it. If the initialization is not done the same way as the loading of the data later, the first touch would not match the reference patterns later. For example, one of my programs, in fact, code 2 originally had a three-dimensional array, but at the beginning it zeroed it out as a single-dimensional array, which nowadays is illegal Fortran. Okay? So it's possible that the initialization of the array does not multi-thread or does not work the same way as the processing of the data later. So first touch can get you into trouble in those cases. The other one then is round robin that simply says spread the pages round robin across my pages, across my nodes. There's also one here, PPM, number of processes per module. The default right now is 1, is 2. If I want to switch it, right now it's 1, but we've got with SN1 we're going to have 0, 1, 2, 3, 4 processors, but we're not sure how this is being handled here yet. So by default it's 2, and I can drop it down to a 1. Now why would I only want 1 thread per module instead of 2? Warren applied this the other day when we put 4 CPUs on a sysad bus instead of 2. The
Saturated bus.
If I'm saturating my sysad bus, I may want my application that's memory intensive, not large in memory, but spends all of its time reading and writing memory. In that case, I may want to leave the other CPU alone so that my sysad bus gives me the bandwidth I need to memory. But by default, it's 2 per node. So in some cases, a 16 CPU system, I may go 1 per node, 8 threads wide, and let the other CPUs get wasted. Anyway, so under DSM, there's also round robin, whether the data is going to be round robin or not, versus first touch. And then there are the next pieces, and this is what I really needed to get to. So those were some of the DSM ones doing with topology information. But the next set of metrics are really, or environment variables I want to talk about, have to do with multi-threaded applications. Now there are 3 types of variables here. The first one is going to be how many threads. If I don't specify anything, there is a default that says like 8 threads wide on the system. But I can change that. And these are done with OpenMP syntax environment variables. The environment variable to control that is MP set num threads. MP underscore set underscore num threads. Now there also may be the application automatically overriding that. So I could have had an application written 2 years ago before this was available, and it's actually going to override that MP set num threads. Now actually I should be careful here. This is the older SGI syntax, and I caught myself too late here. What I really wanted was the OMP variables, and the reason is the compiler that I must be running on. NPE underscore PNVIRON. DSM, MP. There's no OMP environment variables on that man page. There they are. So because of the multiple products loaded, my second man page is the one that probably fits to a newer compiler set. And the one that I wanted was OMP num threads. So OMP underscore num threads. So OpenMP was a standard, and there is an S on there, was a standard, and all the environment variables begin with an OMP. But before OpenMP came out, which was the 7.2 compilers, it was SGI specific to say MP underscore. They will result in the same thing. And what this is static threads. If I say go 8 threads wide, you get 8 threads wide. So static threads simply says you're going to hard code essentially the thread width. Then there is another environment variable here called OMP underscore dynamic. And this is dynamic threads. And here we use SAR data to decide thread width. So when I go to OMP underscore dynamic and make that true, I'm turning off static threads, and then the MP libraries will look at the load on the system and say, I got a 16 CPU system and my queue length is 16 threads or 16 processes, so I better not go 16 wide, that's too much. Now this occurs at the beginning of each parallel region. So if I've got a do loop, before I go into the do loop, I'm going to sample the load on the system with the SAR command, figure out how loaded it is, and then set a certain number of threads to spawn off based upon that load. So in dynamic threading, there's no guarantee that you're going to get those CPUs. Now if I have a program that runs for 3 days in that do loop, I may look at the load of the system at the beginning of the 3 days, spawn a certain number of threads, and then when I'm done, what was I going to say? 3 days later, the load might have changed. So when I spawned the multi-threaded application, the condition of the load was one way, and then as time went on, the load shifted, but my multi-threaded application was not able to adjust to that because it only occurs at the beginning of the parallel region. So with static threads, all the threads are going to have about the same CPU service time, but with dynamic threads, things are going to shift. And the example we saw earlier looked like a dynamic thread group because 2.5 of the threads got all the CPU and the other threads didn't get anything. So OMP num threads and the one right after, or before it, where are we? OMP underscore dynamic.
So what are the problems you need to see in order to be able or to make a decision? You need to
You need to know if your machine's undersubscribed or oversubscribed. So to decide this thread width, we need to know scalability first of all. I'm not going to go 32 threads wide if my service time is going up and my lapse time is going up because it doesn't scale. Then the second thing is less threads than CPUs. So on a 16 CPU system, I don't want 4 of us running 16 threads wide. Because we're not going to get the 16 CPUs.
So you just assign for each of you certain amount of threads?
Different jobs have different scalability characteristics, so each job has to be set individually. But now if I'm undersubscribed versus oversubscribed, that can make a difference. So let me come back to some of that. The first thing then was how many threads. The second one was how to chunk data. So this environment variable is telling me how am I going to break up my array? How do I determine how many pieces and how big the pieces are going to be? And that is called OMP underscore schedule. And that one has both static and dynamic. Not to be confused with static threading and dynamic threading. So here it talks a little bit about it. Values for this variable are static, dynamic, or guided. And let's see, the chunk size is optional. A chunk size of 1 is assumed, except in the case of static. For static, the default chunk size is set to the space for the array divided by the number of threads that are going to process the array. So this OMP underscore schedule is going to say, how do I break up the data? And we don't really care about that. The third one we do care about is how to synchronize. So when I'm adjusting the thread width, I want to know how well the application scales and what the load on the system is going to be like. With this one, I can adjust how I talk between threads depending upon the load. So if my load is less than the number of CPUs, I do one thing, and if the load is greater than the CPU count, I do something else. There are 3 environment variables that I care about in this area, and these are the ones that are going to help my code 2 synchronize, have the most influence on my synchronization time. Question? Okay. The first one is underscore DSM underscore barrier. That is what hardware to use to communicate. What hardware do I want?
I'm kind of confused here, probably lost.
Go ahead.
I don't understand when I have to do this. I mean, what exactly I'm looking at, so it would tell me I need to look at these variables. I mean, I'm sorry, I'm lost.
So we've gotten into these basically because with Perfex, we were able to spot multi-threaded barriers as a problem. The loads and branches and possibly stores were dominating my service time.
Okay.
So that tells me I have a barrier synchronization problem.
Okay.
Okay, so when those are high with perfects, then I want to say, how are these things being done?
Okay.
Okay, so
Alright.
these are the three main characteristics I look at. Okay,
Alright.
so the thread width is something. Maybe they went 120 threads wide and it was a 16 CPU system. So I've got to say, okay, is your thread width fair for that application? And if there's a load on the system, that's also going to affect the thread width. The second one we're not caring about here, but if I'm just explaining because it confuses people, static and dynamic scheduling does not have anything to do with thread static and dynamic scheduling. There's bad terminology intermixed there. But that's basically how do I break up my array. But the third one is the one that I'm really trying to get to right now. So this one's going to say, with a PS, how many PS entries do I see? And this one's going to say, how are they going to talk to each other? So since I have barrier synchronization, if it's a scaling problem, I'm going to drop the thread width down. But if it's not a scaling problem, I'm going to look at better ways to synchronize. Better ways for them to talk to each other, to say, have you finished your work yet?
Okay.
So DSM barrier is the hardware mechanism. It will say, do I want to use floating point? Do I want to use this LLSC, or do I want to use shared memory? Now make a note of this. Shared memory is no longer the default. The documentation has not showed that yet. So make a note of that in your notes. The default now is prefetch operations. And I just found out about this in the past couple weeks. And I should point this out. The environment variable to tell me how all these things are doing is underscore DSM underscore verbose. So DSM underscore verbose, if it's true or set, then the libraries are going to print out diagnostic information about all these different attributes. Okay. Now again, if perfects didn't show loads, branches, stores going on at the top of the list, I'm not going to be concerned about that. Maybe it was false cache sharing. It was perfects that told me barrier synchronization is my problem. So I want to say, am I too wide and I can't scale very well? And that could be to false cache sharing as much as barrier synchronization. And then how do I break up my data? And lastly, how do I synchronize or talk between them? So the floating point, or I'm sorry, the prefetch operation is now the default. The second one uses a unique instruction on the R10K in future called a load length store conditional. And the third one then is saying just use standard shared memory. And I'm hoping with SN1 I get a fourth one here that says use the interprocess communication ports to the other CPUs. Now, if I go to LLSC, there's a stored conditional that's being hidden in here. So some of these changes are going to affect whether the branches and stores are there or not. So DSM underscore barrier. And also the compiler. If you're at a 7.3 compiler, they change the code such that you start having different behaviors where the branches and stores are not visible. So you're always seeing the loads. But depending upon how DSM barrier is set or what compiler you're using, you may not see the branches or stores. For example, in our case, we were not seeing the stores yet because I was a 7.2 compiler. In fact, let me change that now just to see how that helps or hurts. Dot profile. Before I do that, module avail. And I'm going to pick the latest compiler, 7312. I'm not saying this is good, I'm just trying the latest. And a module list shows that I'm presently on a vanilla 7.2 compiler. So I'm going to edit my .profile or put it in the jobs. And it's showing up as a 7.2.1 compiler for the batch environment versus the interactive. So I'm going to load that module instead and go to a newer compiler. And now I'm just going to try submitting again. Again, if you look at code 2mp.nqs, I do have a DSM underscore verbose set, and I have set the barrier to be shared memory, and we have two other parameters that we're going to be interested in. Underscore DSM underscore weight, and also something called MP block time. So DSM weight says, how am I going to talk? Am I going to spin or am I going to yield? If I have DSM weight set to a spin, I am not going to give up the CPU. I will hold the CPU and sit there trying over and over again. It's like, are you there, are you there, are you there for 2 weeks. I can also switch it to a yield instead of a spin. And a yield says, are you there, are you there, are you there? No, hang up and try later. So with a yield, you give the CPU back to the kernel, and then hopefully the kernel will give it to somebody that needs it. So if I'm undersubscribed, if the load is, where was I here? If the load is less than the number of CPUs I have on the system, then there's a good bet that I'm going to get all my CPUs, and a spin would be better. So if I'm the only one on the system, it's my system, no competition, and I can control my thread width, spinning would be better. And that was the default in 6.4. But then they found that most of the origins were going into compute server markets running like craze, where the workloads were higher than the capacity, the loads were bigger than the number of CPUs, and they switched the default to a yield. So when I was at 2 weeks, that was when I was doing a spin for 2 weeks and just sitting there saying, are you done, for 2 weeks. Then we switched it to a yield and said, are you done, are you done? No, give up the CPU. No. And with this giving up is done with a system call known as SGI nap. And the time between the naps is MP block time. So DSM barrier says, what hardware do I use? DSM weight says, do I spin or do I yield? And then block time says, how long do I spin before I do my yield? How long do I try before I do my yield? So if MP block time is small, you're going to get system time. If it's large, you're going to get user CPU time. And we need to take our lunch break. So when we come back from lunch, I'm going to try playing with these multi-threaded options and deciding how many threads wide do I want to go. I'm not going to play with this, but I'm going to basically play with barrier, weight, block time, and num threads and dynamic. 1, 2, 3, 4, maybe 5. Basically 5 key environment variables that can influence my code 2 running better. So we're just going to focus on this one, and these 3. So for multi-threaded applications, these are the ones that can influence how well I synchronize my barriers without rewriting the application. And we're, I meant to go to 12:30. We need to get to lunch now before they close down the food. In fact, some of it probably gone by now anyways.
They're open till 1:15, right?
Yeah, but that's sandwiches and stuff too. So you can go ahead and stop that for lunch. Telling me it was a user routine or a library routine of the SGI. And that's using perfects to identify TLB misses when we talk about large pages. Secondary cache misses we're going to come back tomorrow when we talk about CPU scheduler and miser. And right now we're talking about multi-threaded barrier problems. And we also talked a little bit about false cache sharing. So everything this morning goes back to identifying these 3 types of effects. And what can I do about it? How can I recognize it, and what can I do about it without rewriting the code? So we'll see it. Let's 1:30 thereabouts, 1:30, quarter to 2 technically, but let's try between 1:30 and quarter to 2. It gives you 45 minutes in tuning and just recognizing the effects. The hardware counters identifying that the effect is occurring, and then what can we do at the command line level? I do see, for example, we do have some code 2 MPs running. We got 1, 2, 3, 4, 5, 6, and probably 5 threads wide. Not sure. They look like they're all, well, they're different process groups. What were you gonna say? 2 wide. Two wide. Yeah, when I went over here, process groups, you can see by process group that they're 2 wide 3 times. Okay. So that's helpful. Every thread with the multi-threaded application will have the same process group ID. Again, the CPU scheduler is distributing CPUs by process group. So they're trying to equalize every process group to get the same amount of CPU time. So I wanted to go back. Let's see if I've got an output here of interest. And just take a look at 440 here. And now when you multi-thread, you've got all these underscore MP-do type of routines. That's what the library is creating. And now here. So here is the beginning of our DSM underscore verbose variable. This was another one that I didn't really mention earlier, but is relevant to us. It doesn't affect anything, but it tells me what the libraries are doing. So in this example, this particular run, it said it used a block scheduling or simple scheduling. What we're talking about here is how I chunk my data. So it's calling static means simple scheduling. And then saying that we're just going to use block scheduling for that particular scenario. Then I see it's a 16 CPU system and we're going to spawn 4 threads. I did not change the DSM PPM one, so it's 2 processors per memory, or 2 processes on each node board. Also see migration is off. We'll come back to migration on Friday. It's also using first touch placement, so as it initializes the array, that's where it's going to place the page. If I had the loop not vector or not parallelizing, I could have a single CPU try to zero out the whole array, and all that memory would then get allocated on that node board. And then when I hit the multi-thread portion of the application, all those other threads would not have their data there, they'd have to pull it in. Also telling me my stack size is at a default of 4 to 16 megabyte on the stack size. You can up that, there are a couple parameters to do that. And also it's checking for overflow on the stack to make sure that I don't step on things in the stack. Overflow it. It's a NUMA machine, IP27, and then it created what was called an MLD, a memory locality domain. So it's taking all of my topology information and creating a packet for it. So it'll tell me things like all these DSM variables, whether migration's on or off, what my touch policy is, that sort of thing.
What the MLD is again?
MLD stands for a memory locality domain. It's basically placement information that the user can give the operating system as clues as to what it wants. So when I use dplace, the dplace command creates an MLD for me. Or in my C, I can actually manipulate it at the library level rather than at the command level. So the MLD, memory locality domain, contains information like how many threads per module, what's my allocation scheme, first touch or round robin, all these sorts of information. Do I have migration on or off? What's my page size? All that stuff is wrapped into a single packet of information that we call an MLD. And then when I ask the operating system, I'll make system calls and point it to this MLD, and then the operating system will try to achieve that placement information. So with the MLD, it's got like what CPUs I want to attach to, where I want my memory placed, and all that sort of information. So it's unique to a topology-based machine, and only IRIX has that capability right now. So it said it created and placed an MLD, topology free, it was advisory, and here's what the attachments were. We're going to use node 1 and node 2. It was a 4-thread process. And it gave me a few other pieces of information. Here's my, this we don't really care about here. But here's my page size. So everything is at 16 KB, which was the default. And now here's where we left off before lunch. The weighting of this application is going to be a yield. We have spins and we have yields. Okay, if it's the spin, going back to this right here, the spin is going to give me high user time, whereas the yield is going to give me high system time. So if it's a spin, I'm sitting there holding the CPU in my MP library routine, MP slave wait for work, saying, are you done, are you done, are you done, are you done? So all that shows up as user time. If, however, I switch to a yield like this one is done, then I say, are you done, are you done? Nope. Give up the CPU, and that was an SGI nap. So with an SGI nap, I am giving the CPU back to somebody else. For Cray people, it was called resched. The resched system call was a way to say, here's the CPU, give it to somebody. The whole purpose of the system call was to yield the CPU up so that somebody else can get it. So once I start yielding, I'm going to start making SGI nap system calls, which is going to result in my system time going up. But if I give the CPU up and it goes back to the program that needs it, my throughput can also be going up. So my system time can be going up and my throughput's going up because I'm not spending as much time spinning saying, are you done, are you done, are you done? But I'm saying, are you done? Give it to somebody else and then they can get done with it. But there's no guarantee when you do an SGI nap that the thread you're trying to talk to gets that CPU. That's the disadvantage with multi-threading right now, is that the MP libraries, which do their scheduling decisions, do not talk to the CPU scheduler to get agreement that we want this work done. So when I do an SGI nap, it may give it to somebody completely different than the thread that I'm sitting there waiting on. There's no guarantee that it goes to the process that I'm trying to talk to. So a yield, again, if I was oversubscribed, a yield is better because if I give up the CPU, there's more processes than CPUs and I can give it to somebody else. But if I'm undersubscribed and I do a spin, then my service time is going to go up. But if I am undersubscribed and do a yield, then my system time is going to go up. So if I do an SGI nap and yield the CPU, but there's not enough processes to keep the CPUs busy, what's going to happen? I'm going to get the CPU right back, and then I thrash on SGI naps. So if I'm oversubscribed, the yield works, but if I'm undersubscribed, my system time is going to go up even more. And that's where you get into block time, or we called it MP hold time in the older days. In fact, Cray libraries, we'd look at the load level and adjust our MP hold time based upon what was going on in the system. So MP block time says how long between my SGI naps. How long am I going to spend waiting to hear from that other process or other thread before I do the yield? So if my system time is going up and I'm doing SGI nap yields, I can increase my block time, which would slow down the SGI naps, and then my system time would go down. So adjusting block time balances between the system time and the user time. So if the block time is going down, the system time is going to go up. If the block time is going up, my user time is going to go up. So it's different scenarios. And I should take a look here in a minute. Let me just see what else we have here. It also mentions the master stack size before it hits limits, a few protection information. Some of this is fairly new. And remember, I also switched library sets. I've gone from a 7.2.1 to a 7.3.2.1 compiler product. So these verbose messages have changed slightly. I also see something called gang scheduling. Gang scheduling says that all threads will be connected to the CPU at the same time. For me, it was a Cray terminology for T3E. We would connect and disconnect the whole gang of threads at the same time. And when they're on the CPUs, they're all connected together and are able to communicate without playing phone tag. OpenMP obsoleted gang scheduling. It's not part of the OpenMP standard. And in fact, gang scheduling will hurt you in IRIX. It will be penalized as a gang, because they don't want gangs to beat up on the interactive user. So in this example, gang scheduling has been turned off. And also then dynamic threads was on. So dynamic threads was saying, based upon the load of the system, instead of static threads, OMP dynamic was set to true, which says, look at the load of the system and use that to figure out how I'm going to spread my work. And I also see that it's using the fetch up for barriers. Before I was using shared memory, so that was the DSM_barrier. Okay, so I know that they've set up a few of these things. They've turned gang scheduling off, they've turned dynamic threads on, they've got hardware barriers, fetch ops for the hardware to communicate between things. And let me just go down here now, let's see what we had here. So here my program took 207 seconds for this particular run. 175 of it per thread. So in tuning, my elapsed time is getting shorter, but my service time is going up because I've got more time spent playing phone tag, and my system time is going up because I'm spending more time with yields with SGI naps. In fact, here we can start to see now some of the system times starting to go up where they weren't there before. Let me see. ACCOM-N code 2MP. ACCOM-N code 2MP. -T to split user and system time out. So here are some threads that are coming in with system time of 0, and some that are coming in at 5 seconds, for example. Let's see if I can find a big one. Oh, not there yet. I'll try it again. So here now, look at, here's some applications I ran where the system time now is in the 20 or 30 second range. So my elapsed time got a little bit worse. My system time was in the 36 second range instead. Let's see if I can find any others. Oh, didn't find too much more. Let me try a SAR command real quickly. And the system time now is the second field here. And during lunch, I ran some workload and look at my system time went up. Typically it was 0 or 1%. Even right now we're at the 1 or 2%, even though Warren's got those code 2s running. But during lunch when I fired off my workload, the system time went up to 8 or 9%. So if I go back to my workload, the thing that was influencing that was this MP block time. Instead of 4 threads wide, I'm just going to take a sample here and do 12 threads wide. So I set block time shorter, and I'm going to keep verbose on. I'm going to make sure MDC gang is off, and I'm going to go to, I'm just going to leave that alone. Before I do that now, SAR 1 space 15. Oops. So my system time is 1 or 2%, 0%, 31% per user. No I/O going on, lots of idle time. Now let's see what happens here. This point where I wish I did have share too, so that I could get through the system faster than Warren. Waiting for my compile to finish. It is. Well, I'm queued up. I'm not even running yet. Going to override it. Let's see this get res request ID now. Still queued up. Okay, so I now have that program actually running. I just overrode NQE and said I don't care what the loads are like, just start up that particular job. And that was basically a skid now command. schedule request 459 now, run it now. Also referred to as preemptive scheduling. Okay, so I'm compiling now. Now looking at top, I've got 91 processes on the system. 79 of them are sleeping, 1 is stopped, and 11 is running. So I've got a 16 CPU system and I'm still undersubscribed. 38% idle, 60% user, 2% kernel. What I'm waiting for is my compilation to finish, and I expect to see system time go up once that code 2MP actually starts running. Now, who remembers the command to look at system time? Par. So I'm going to, while we're waiting, I'm going to do a par-little-s, big O, raw PA file. And I'm just going to run it like that, and I'm looking at the whole system right now. I'm not looking at it on a per process basis. I want to see the whole system. Just blow it up. I wanted a baseline before everything else started. So right now I'm waiting for my codes to actually get into the system. Did they fail? Looks like it failed on me.
I didn't do it, I promise.
No. It's probably a memory limit. Because remember, I upped the thread width, and upping the thread width, not enough space to sproc. So because I upped my thread width, my memory limits and my stack limits were no longer valid. So let me see what I've got here now. Yes. Instead of going 12 threads wide, I'm just going to go 10 threads wide. And that one failed too. I asked for too much probably.
That's 4 gigs.
This is the hard part about a batch interface. I need to have an idea of how, I have to run it successfully first to know how big it's going to be. If I change my thread width, that's also going to affect this problem. Let's still come back here. So here's what's going on in that particular job. It's getting us, when I'm doing the limit command, stack size, it can't remove the limit. Limit exceeds allowable limit. So that's that stack limit that I was specifying, the -S option. Let me see if I can get that closer. Here I was trying to do limit stack size unlimited as well. Let me just get rid of that.
That's interesting, because that would have overrode the previous one, wouldn't it?
But it didn't allow me to do the unlimited, that's correct. It was failing on that one.
Oh, because of the other one?
And I wasn't able to go unlimited. I don't know what the limit command output looks like there.
Okay.
Let's see if that one comes back. 463. So 463 is running right now. And here I've got my memory limit on a per process base at 2 gig. 2 gig for the request limit, and I'm only using 55 meg right now. It isn't showing me my stack, is it? There we are. Here's the stack size, and that's where I asked for 1.5 gig. See if the application is running yet. So once I up my thread width, I then needed, when I spawn copies of this process, all the threads, then they're going to have a larger stack. So for example, code to MP, we were at, we'll have to run a single threaded version, but see here they're at 33 meg. As soon as my compiler finishes, we should get past that.
What did VE read? Oh,
There we are.
no.
So note now, my base memory use is still 23 meg, but each thread that I've spawned off, because I've gone wider thread width, instead of the 33 meg when you were like 2 wide, now that I'm 8 wide, it's 111 meg that I'm reserving. So if it was 111 meg times 12 of them, that's where, or 10 of them or whatever, that's where you get a limit number. Also note now that my system time is also going up a little bit. Not as bad as I thought it would be, actually. And again, this is part of the new libraries. But now I'm going to do SU again, and this time do a bar-s-o raw1 file. And collect a little bit of information about the system calls that are going on right now. That'll be good enough. SAR. Space 15. So my system time went up about 2%, not too bad. 80% user time right now. Of course, the question is, how long is it taking these things to get done? Let's just see if we got any ACCOM data. And we were in the 260, 270, some of the ones that these running right now, and they're too wide, it looks like. So you can kind of see them grouped together. So those are coming in at 269. Question?
Width of 2.
What's the question?
I said the width is set to 2.
Yeah. And again, without parent PIDs, it's kind of hard to tie the two together. Actually, I think it's these 3. Yeah. So all my work is spread between these 2 threads, and then this is my master thread watching everything. Actually, though, no, that's the wrong 3. It's these 3. By the start times. And they all have the exact same elapsed time.
The last, what's the last
There's like 4
code?
sets right there.
This one here,
Uh-huh.
that's my user time.
Oh, so one of them.
It kind of hasn't up here shown it. But one of them is a sleeper. That is the master thread that's simply saying, you guys do the work and I'm going to check between you. So it's a shepherd that isn't doing any of the computational work. So he asked for 2 threads wide. He got 1 master thread. And then the 2 threads themselves, one did 197 seconds of work and the other one did 267 seconds worth of work. And again, Perfex is going to tell me what that actually was, whether it was barrier synchronization or computational work. So there was a 3-thread wide one. I'm looking at the numbers, 265, 265. This was the one that blew up because I didn't have enough memory declared. 271, 265. So when I'm going 2 threads wide, most of my application runs are coming in under the 228 or 288 that I had before. So now that we've gone dash 03, I'm sorry, dash PFA or APO, they both do the same thing now. Now I'm starting to see 260 approximately wall clock time, but then when I add up the service time, it's going to be more. So for example, this one that was at 266, it's 264 plus 195, 360, almost 450 seconds in that example. CPU service time. So the difference from the 288 that we had here, 290, to the 450, 290 from that, 160. So there's 160 seconds of barrier syncing. assuming I had Perfect's data to confirm that.
Those 4050 is, you add it up between
I added them
each
all
of
up.
the thread.
Right.
But now you got some data from your codes, and those kind of probably, let me see what's this time. This is CPU. CPU is getting even lower.
Sure. So as I go wider and wider in my thread width, I'm going to have more barrier problems. The more people on the phone line, the harder it is for them to communicate to each other. Let's see if I've got any reports now. This looks like the oldest one I have. So this is where we were before. 543 seconds of empty slave wait for work, and that's my barrier synchronization. And somebody comes to me with a report and I see libmp at the top of the list, that's an SGI library. And then right underneath it was CLIN doing its 206 seconds worth of actual CPU service. So that's kind of what I'm showing there is there was 290 seconds of actual work, 450 seconds total service time, so there was 160 seconds that were non-productive work. And in this case, it looked like barrier synchronization. Let me try something else here. I wanted to see if the system time's going up. In my last couple of classes with 659, SGI naps were doing very bad on system time. I was getting system time up to 80% by what I'm doing right now. Let me just go to the first one. See a whole lot of it. This is the 17th. Today's the 18th. It's like there was stuff running in past midnight. And here's my system time. I really can't see it yet. But my system time was in the order of 2 to 3%. Now it's getting up to 7 or 8%. So these are the spikes where my system time is starting to go up. It's not as bad as it's been in older releases. All that workload's done now.